So chapter 3 is on functions. Section 3.1 is on functions and functional notation. So first, I'll give you several different concepts to describe what it means to be a function. So the first idea is the idea of a dependency statement. So the dependent variable is completely determined by some independent variable. Y equals X. Next concept of a function is the function machine. So in the function machine, you have some input, and then the function machine does something, and it gives a unique output. And so the input here is called X, the independent variable, and the output here is denoted usually by Y. It is the dependent variable. You have a unique output, the same input. So you can think of this as being like a candy machine or something. And if you select some input, 2B or something, then you expect that once you select this input, that your output will always be the same. You get your candy bar, your favorite candy bar. You don't want that once you select it, you get something different. You get coal or something. You expect that if you select B2, you get this candy bar. And so that is the idea of a function. If you input this, if you input the same X at differing times, the function machine, whenever you give the same input, you should have the same output. Ordered pairs. So a relation, R, is just a set of ordered pairs. And it turns out that a function can be thought of as a special type of relation. A relation is called a function if the set of ordered pairs have distinct first coordinates. When I say distinct first coordinates, I'm assuming when I write my set that I don't have duplicate ordered pairs. I've gotten rid of the duplicate ordered pairs. And so if I've gotten rid of those duplicate ordered pairs, then, because that's the way you should write a set, then if the set of ordered pairs have distinct first coordinates, we will call this a function. So let's look at the idea of a function by way of sets. So let X and Y be sets. Let this be a subset of X, and so we'll denote this set DF. So let this be a subset of X. Then F mapping X to Y is a function from X into Y if F is a subset, of the Cartesian product between X and Y. Okay, 1 second. See if I can do that a little better. Okay, such that for all X in the domain of F, there exists a unique Y in the set Y, such that the ordered pair XY is in the set F. In other words, if the ordered pair x comma y1 is in the set F, and if the ordered pair x comma y2 is in the set F, then y1 equals y2. I should note that the set X is called the corange of F. The set Y is called the codomain of F. F of the set A denotes the following set of all f of x such that x is an A. We will denote the range of F, abbreviated by this, as f of x. Y equaling f of x denotes the image of x under the mapping F if the ordered pair xy is in the set F. So pictorially, we can think of this as follows. So we have here the set X and the set Y. We call the set X the corange of F, the set Y the codomain of X, of F. We will call F here a function if we have the following. So a rule F mapping X into Y is a function if for every X in Y there corresponds a unique Y in the set Y, and this Y is called the image of X under the mapping F, and is denoted by Y equals F of X. Okay. The set of all images, well, the set of all images of this subset domain of F of the corange is called the range of F. So this is the set of all x's, well, the set of all y's, such that f of x is equal to y for some x in the domain of F, and that's the range. The domain must be, well, is such that it has an image under the map. Let's look at this visually. And so there's another way to visualize the idea of a function. So we have what's called the vertical line test. So suppose I have some curve in the plane. And so, and suppose that I have this relative to some coordinate system. Then, if this curve, well, if I can find a vertical line that intersects this curve in more than one point, then I say that this does not pass the vertical line test. This curve does not pass the vertical line test. If this curve doesn't pass the vertical line test, then it is not the graph of a function. So this is not the graph of a function because it does not pass the vertical line test, because I found a vertical line that intersects this curve in more than one location. So it intersects any sort of vertical line. It intersects some vertical line in more than one location. So even though in some it only intersects at one location, if you can find at least one vertical line that intersects this curve in more than one location, then it does not pass the vertical line test. It is not the graph of a function. However, if you can find, so suppose again, this is a curve in space. Suppose I start here and keep going, and relative to some coordinate system. Then if every vertical line intersects this curve in at most one location, and so it can either intersect it at no location or in one location. So every vertical line intersects the curve at one point. Then we say that this curve passes the vertical line test. If a curve passes the vertical line test, then this curve is the graph of a function. In other words, the graph of, well, I'll tell you what the graph function is. The graph of the function f is the set of ordered pairs such that x is in the domain of f and y equals f of x. And so there exists, if my function, if my curve passes the vertical line test, then there exists some function f such that y equaling f of x is such that the graph of y equaling f of x is this curve. Okay. The domain of f is a set of all x in my corange x, such that there exists a unique y in my codomain, such that y equal f of x. As we said above, the set of images of a set is denoted by im. And so the range of f is the image of the set domain of f. Sometimes we have a function, but it's just given by some rule, and we don't explicitly tell you what the domain is. If that occurs, then we will assume that it's endowed with the natural domain. The natural domain is the largest possible domain. So it is the set of all x's for which f of x, for which y makes sense. So in general, we don't want to divide by 0. And in this class, we'll usually want that our functions are real valued. So we do not want to take even roots of negative numbers. So that's the general rules that we will, our guidelines that we will follow to determine a natural domain. So let me do on page 290, problem number 13. Assume that all variables represent real numbers. Determine whether each equation determines y to be a function of x. And so, in this case, is y squared equaling x a function? Is y a function of x? Well, if you look here, suppose you took y equaling -1, then x is 1. And suppose you took y equaling +1, then x is equal to 1. So what that means is that if x is 1, y could either be 1 or -1. But we don't like that if you input, B2 in your candy machine, sometimes you get your candy bar, sometimes you get a piece of coal. So therefore, this is not a function. So y is not a function of x. Okay. So y here is not a function of x. Let me do problem number 15. Y equal x squared. Well, if you take any number and you square it, you'll always get some answer, and it's unique. If you go and plug something on your calculator, say you hit the squared button, it gives you an answer. And that answer is always going to be the same answer, no matter if you do it at 3 in the morning or 5 in the afternoon. It'll always give you the same answer. So therefore, yes, this is a function of x. So y in this case is a function of x. Okay. Let me do problem number 22. X plus y in absolute value equals 7. Okay, is this a function of x? Is y a function of x? Well, if you put in, let's say for x 0 and for y 7, 0 plus 7 is 7, absolute value 7 is 7. And let's put, again, the same 0 for x, but let's do minus 7 for y. 0 minus 7 is a negative 7. Absolute value negative 7 is positive. And so both input of 0, output of 7, input of 0, output of negative 7, they both satisfy this equation. So therefore, again, this is not good. For function machine, you don't want occasionally your candy bar or a piece of coal coming out. You want it always to be, and so no, y is not a function of x. Let me do problem number 28. Let the function f be defined by the equation y equal f of x, where x and f of x are real numbers. Find the domain of each function. Okay, so in this case, we just have a rule, f of x equaling radical 2x plus 3. We haven't said what the domain is, so we'll assume that it's endowed by its natural domain, the largest possible domain, such that if you input a value, your output will be some real number. And so let's input some real number and get an output of a real number. Well, we're not dividing by 0, so I don't have to worry about dividing by 0, but I do have to worry about taking the square root of a negative number. And so to determine my domain, I do not want to take the square root of a negative number. So I want that what's inside the square root is greater than or equal to 0. Subtract 3 from both sides of my equation. Divide by 2. And so let's just in case I need more space. Actually, I probably didn't. And so I have here that x is greater than or equal to negative 3/2. Dividing both sides of my equation by 2. And so the domain of my function f is just a set of all x's such that x is greater than or equal to negative 3/2. We can write this also in interval notation. And so the domain of my function f is just the closed interval from -3/2 to infinity. Okay. And either one of those is a correct answer. Okay, let me do problem number 34. So in this case, I want to determine the domain of this function. Well, in this case, we're taking a cube root, which is not an even root. It's an odd root. 3 is an odd number, not an even number. And so, the cube root of a, let's say 20, cube root of 27 is, or cube root of 8 is 2. But the cube root of -8 is -2. So you can take cube roots of both negative numbers. Therefore, it's okay to take a cube of a negative number. And so there's really no restriction on x. You can have any number, and it can be subtracted from 5, and you can take its cube root. Therefore, the domain of my function is just a set of all real numbers. It is all numbers from -infinity to +infinity. And that's the domain of my function. Oh, okay. Let me do problem number 41. So in problem 41, I want to find the domain of this function. So first, let me rewrite this function. Let me factor the denominator. Well, this just factors into, this is a monic quadratic trinomial. So I'll bring down the x. I have a negative, so let's bring down the negative. Times negative is positive. I want two whole numbers whose product is 5 and whose difference is 4. So 5 and 1. Okay. So now, and I'll put the root with largest absolute value first. So now I want to find the domain of this function. So in this case, we're not taking even roots of negative numbers because, well, we have no even roots. And so we are, however, possibly dividing by 0. And so we set my denominator to 0 and solve for x. So by the zero factor property, I set each factor to 0 and solve for x. Add 5, subtract 1. And so the domain of my function is just a set of all x's such that x is not equal to -1 or x is not equal to -5. It is the union of the following open intervals. It is -infinity to -5, because I don't want to union. I don't want to include -5, so -5 to -1, because again, I don't want to use -1, union -1 to infinity. And so that's the domain of my function written in interval notation. And well, you can use I notation unless they specifically say to use a type of notation. Okay, let me do problem number 53. Let the function f be defined by y equals f of x. Oops. 1 second. Let me just look. There's a question. I'm pulling up the question. It'll take a second. Okay, let's see if the question comes up. Okay, why are you not showing? Oh, the 5 will not be positive. Oh, okay, so let me just check. Oh, that's an error. Thank you. Sorry about that. Thank you. That is a typo on my part. Thank you very much for that remark. Yes, bad error. Okay, so the domain is everything except for 5, positive 5, and negative 1. Okay, so thank you very much. So negative infinity to negative 1, negative 1 to 5, and 5 to infinity. Okay, sorry about that. So it includes everything except for negative 1 and positive 5. Okay. Yes, that was not a good thing to do. Okay, so uh, uh, so let the function f be defined by y equal f of x, where x and f of x are real numbers. Find f of 2. So let's determine f of 2. F of negative 3, f of k squared minus 1. So first, let's determine f at 2. So wherever I see an x in this formula, I'll replace x by 2. 2 plus 4 is 6. I can divide both the numerator and denominator by 2. So f of 2 is equal to 1/3. Okay, let's do the second part. Get some more room here. So I want to figure out f at negative 3. So let's just replace x here by negative 3. Negative 3 plus 4 is 1. 2 divided by 1 is just 2. So f at negative 3 is 2. Next, let's figure out f at k. So wherever I see an x, I'll replace x by k. And so f of k is equal to 2 over k plus 4. And that's your answer. And lastly, let's determine f at k squared minus 1. And so let's replace here x by k squared minus 1. And so I have 2 over x, k squared minus 1 plus 4. And so this is equal to, I'll just move this down slightly. So f at k squared minus 1 is equal to 2 over k squared. 4 minus 1 is 3. And that is your answer. Okay, so before I do the next problem, let me give the concept of, or the notation really, of difference quotient. So if I say that I want to determine the difference quotient, then I want to determine the following quantity at x plus h minus f at x, all divided by h. And I want to simplify this so that I cancel out as many h's as I can. And so cancel out so that I'm no longer dividing by problem number 62. Evaluate the difference quotient for each function. And so I want to evaluate f of x plus h minus f of x, all divided by h. Okay, I'm gonna need a little bit more space. So let me do another page here. So this is going to equal. So wherever I see an x in this function, I'm going to replace x by x plus h. So I'm going to replace x here by x plus h. I'm going to replace x by x. So I just get x squared minus 3. And I'm going to divide by h. So this is f of x plus h minus f of x, all divided by h. So let's simplify this. So by the special product formula, x plus h quantity squared is x squared plus 2xh plus h squared minus 3 minus, let's change all the signs inside the parentheses since I have a negative sign outside the parentheses. So this becomes a negative x squared plus 3, all divided by h. So now let's see if I can do some cancellation. Well, the x squares cancel and the 3's cancel. So this is equal to 2xh plus h squared, all divided by h. Okay, so it's looking simpler. Now let's factor out what's in common in the numerator. Let's factor out, let me restate that. Let's factor out the h that is in common in the numerator. Even if there were other terms, I would, the common factors, I would leave them there. I really just want to factor out the h. So what remains after I factor out the h, 2x plus h divided by h. The h's cancel. And you get 2x plus h. And this is my difference quotient. Simplified. And notice that when I've written this, I'm no, and that's the form that I want to write my answer in. Okay, let's do the next problem. Problem number 70. Again, I want to find the difference quotient, but in this case, it's for the function f of x equal 1 over x. And so, the difference quotient is f x plus h minus f x all divided by h. So, I replace x in this formula by x plus h. I replace x in this formula by x. And so I have the following. Now, I have two fractions. I want to somehow simplify them because eventually I want to be in a situation where I can cancel out this h, because that was the goal in simplifying difference quotients, to somehow cancel this h. So if I look at this, well, in order to subtract two fractions, I want to find the least common denominator, rewrite everything as equivalent fractions with the least common denominator, and then simplify. So the least common denominator in this case is times x plus h. So let's multiply and divide by x. Let's multiply and divide this term by x plus h. And so I get this is equal to 1 times x is x. Let's write this all over the common denominator, x plus h. And now I have here a negative 1 times x plus h. So let's multiply that inside the parentheses. So we get a negative x minus h. And let's rewrite division by h as multiplication by its reciprocal, 1 over h. The x's cancel. And so I get that this is equal to negative h over x plus h times 1 over h. The h's cancel. When I say they cancel, I mean you get a 1. And so this is equal to negative 1 times 1 is negative 1 over x plus h. And that is my difference quotient. Having an h in the denominator is still okay. You just wanted to cancel out the h's here. And that's what I mean by simplifying.